Subtopic 1.3 Factors affecting reaction rate. The learning outcomes for this video are: A. Explain the effect of the following factors on the reaction rate. 1. Concentration of reactant, 2. Pressure, 3. Temperature, 4. Catalyst, 5. Particle size. B. Illustrate the effect of temperature on reaction rate using Maxwell-Boltzmann distribution curve. D. State Arrhenius equation, K equals A exponent negative EA over RT. E. Explain the relationship between temperature and activation energy to the rate constant based on the Arrhenius equation.
You have already met the 3 requirements for chemical reactions to take place effectively. These are: the reactants, atoms, molecules or ions, must collide with each other with the correct orientation and with sufficient energy. When the reactant concentration in solutions increases, the reaction rate also increases because there are more reactant particles in a given volume, so they collide and react more frequently. When the pressure of reacting gases increases, their concentrations also increase. If there are more molecules in a given volume, they will collide and react more frequently, so the reaction rate increases. When the surface area of a reactant is increased, for example by powdering a solid, the reaction rate also increases, as there is greater contact between reactant particles, so more collisions take place per second. When the temperature increases, the reaction rate also increases, because molecular kinetic energy increases as the temperature rises, thus increasing the number of molecules that collide with energies greater than the activation energy. The other result of temperature increase is an increase in the number of collisions per second. Catalysts increase the reaction rate without themselves being used up. They function by creating alternative reaction routes via intermediates with lower activation energies. As a result, there are more molecules present at a given temperature that have sufficient energy to react.
Must remember that for a chemical reaction to occur, the particles must collide. An increase in the number of particles per unit volume increases the chance of their colliding. Thus, a higher concentration of reactants leads to more effective collisions per unit time and causes the increase of the reaction rate. In the gaseous state, a measure of the reactants' concentrations is their partial pressures. When we increase pressure, the particles have less space to move around. As a result, they collide with each other more often, and the reaction rate rises. Similarly, by decreasing the pressure, the particles are further apart and do not collide with each other as frequently. So, the reaction rate decreases. In heterogeneous systems, the rate of reactions additionally depends on the area of contact between the phases. The greater the size of the contact area, the higher the reaction rate. Since many small particles have a much larger area than one large particle having the same mass, by decreasing the reagent's particle size, an increase of the reaction rate is attained. If the particle size is extremely low, a reaction normally proceeding at a moderate rate
For most reactions, the rate of reaction increases exponentially with temperature. As the temperature increases, the average kinetic energy of the particles increases, resulting in more collisions per unit time. More importantly, when the temperature is increased, there is an increase in the total number of particles with energy equal to or greater than the activation energy. small increase in temperature usually brings about a large increase in the rate. Roughly, the rate of reaction doubles for every 10 degrees Celsius rise in temperature, as shown in the following Boltzmann distribution curve. At the temperature T1, the number or the fraction of particles having energy equal to or greater than the activation energy is given by the area ABC. At T2, where T2 equals T1 plus 10, the number of molecules having energy equal to or greater than the activation energy approximately doubles, as given by the area ADF. Generally, the rate of reaction approximately doubles when the temperature is raised by 10 degrees Celsius or 10 Kelvin. This suggests an exponential relationship between rate and temperature. The relationship between rate constant and temperature was first proposed by Svante Arrhenius, a Swedish chemist, in 1889. It is now called the Arrhenius equation. K equals A times the exponent of minus EA per RT, where K is the rate constant, EA the activation energy of the reaction, R the gas constant, and T the absolute temperature. The quantity A is called the frequency factor, which is related to the frequency of collisions with the correct orientation. The term exponent minus EA per RT refers to the fraction of molecules with energy equal to or greater than the activation energy. The Arrhenius equation shows that the rate constant is directly proportional to A, and therefore to the collision frequency. In addition, because of the minus sign associated with the exponent EA per RT, the rate constant decreases with increasing activation energy and increases with increasing temperature.